Hey everyone, this is section 1.4, continuity. Okay, so here's our FLT. Given a function, I will be able to determine and justify where a function is continuous and discontinuous. So while you guys are writing that down, remember, so what we've uncovered so far is what a limit is and how to find it numerically, graphically, and analytically. So how does this all connect with this continuous, discontinuous stuff, right? Okay, so here we go. So first graphically, because that's probably the easiest thing to understand. Okay, so let me give you an example. I'm going to give you some examples of continuous functions. Okay, so this right here is a continuous function. This right here is also a continuous function. This right here is also a continuous function. Okay? But this is not a continuous function. Here we go. One more time. Okay? This is not a continuous function. I'll give you one more. This is not a continuous function. So just visually, if you notice, a continuous function is basically when you never have to lift up your pencil. Okay? So if you never have to lift up your pencil, it will be a continuous function, right? But if there's ever a moment where you have to lift it off of your paper, it would be a discontinuous function. Simple enough? Okay? So how does it work formally, right? Because we can't use that type of justification, like, oh, I lifted up my pencil, right? So here we go. Write this down. Play when you're ready. A function is continuous at a number a if all three conditions are met. So these are the three conditions, okay? F of a has to be defined, the limit has to exist, and they both have to equal. Okay, so let me illustrate this for you. F of a, actually let me draw a graph for you. So here's a. F of a has to be defined, meaning exactly at a, there has to be a defined point. Okay? Number two, the limit has to exist. So okay, actually let me draw like this. This is defined. The limit has to exist. But three, notice how the limit has to equal the defined function. So I'm going to fix this picture a little bit. This is what continuity is. When the limit, when you're getting arbitrarily close to a number, if it meets up to where the function is defined, you know it's going to be continuous. Because if you take a look at this graph here, even though there's a dot, really what you're seeing is you're just seeing a fluid graph with no gaps in between. Okay? So this is the formal definition of it. It has to be defined, the limit has to exist, and the limit has to exist right where the defined function is. Okay? How do we put this into action? So again, we're going to try to put on all three hats, numerically, graphically, and analytically, okay? So here we go. Graphically, this is how it looks like. Okay, you have a graph, you get arbitrarily close to some value, but you also know that it's defined at that exact same value, so it creates a fluid graph, which is the reason why we say, when you don't lift up your pencil, it's always continuous, okay? So here we go. Here's example 1. Draw this picture and play when you're ready, okay? So here it's asking us at which numbers is f discontinuous but also y. Okay, so we assume that this graph here, this blue graph, is the function f. So where is it discontinuous? So while you were drawing this out, where did you have to lift up your pencil, right? So eventually you have to lift up your pencil right there at 1, at 3, and at 5, right? At 1, at 3, and at 5. So at x equals 1, at x equals 3, and at x equals 5. I'm leaving space in between so we can explain it, okay? So here we go. That's the easy part, right? How you justify it is the important part. Remember, you cannot say it's discontinuous at 1, 3, and 5 because I lifted up my pencil. Okay, that's not a mathematical way of proving or explaining why it's discontinuous. So when a function is discontinuous at a value, that means one of these rules were broken. So you have to figure out what these rules are, okay? And again, you want to try to memorize these. Look back if you need to, but slowly pull away from it, okay? So here we go. We go in order. So remember, number 1, that means f of a is defined. Number 2 is the limit exists. And number 3, the limit equals the defined function. Okay, and that's just a very casual way of writing it, okay? So let's look at x equals 1. Okay, why was it discontinuous there? Which rule did it break? So let's take a look at number 1. Is f of 1 defined? Is there a point that's defined at 1? So if you notice, there's nowhere around it where there is a point that's defined at 1. So it actually broke rule number 1. So f of 1 is not defined or undefined. Okay? Therefore, f is discontinuous, okay? I'll write over here. At x equals 1, f is discontinuous since f of 1 is not defined. Now, the number 1, I'm putting it there for reference. You wouldn't write that on your paper, okay? Okay, let's move on to x equals 3. Let's go down the list. Number 1 is f of 3 defined. Is there a point at 3? There is, right here. It is defined, right? So I'll put a check mark there. It passes that test. Number 2, does the limit exist as x approaches 3? Okay, so take a look. I'll do this in red and green. If you approach 3 from the left, and if you approach 3 from the right, do they meet up at the same value? Okay, notice how they don't, right? So here we can say the limit does not exist since the limit of f of x as x approaches 3 from the left does not equal the limit of f of x as x approaches 3 from the right. Okay, if a limit does exist, they would actually meet up at the same value, kind of like right here. The limit as x approaches 1 would exist, okay? So again, when you're trying to prove something is discontinuous, all you need is one case, right? So therefore, it breaks rule number 2 here, right? Now go ahead and do number 5. Play when you're ready. So here, number 1, f of 5 is defined. It's this point right up here. So we move on to number 2. Does the limit exist as x approaches 5? So as we get closer to 5 on both sides, does it approach the same value? It does. So we go to number 3, but notice how the limit of f of x as x approaches 5 definitely is not the same thing as f of 5. They have two very different y values, okay? So therefore, it's discontinuous there, all right? Okay, so here's example 2. Write it down, play when you're ready. Here it says, where are each of the following functions discontinuous? Okay, so where is it discontinuous? Am I missing a part? Okay. Okay, so the easiest thing that you can do, since this is just a function, you try to see where rule number 1 is broken. Where is f of a not defined, right? How do we break this rule? So if you take a look at this here, the biggest telltale sign is when you're dealing with a fraction, you know something can go wrong down below. Okay? If something is undefined, right? What x value would make that undefined? 2, because if you have x as 2, 2 minus 2 would give you 0 at the bottom, which makes it undefined. Okay? So there you go. That's usually the easiest thing to do to spot if you have a fraction, right? Notice here, right here, there's a hole. So it breaks rule number 1. It's not defined anywhere, right? Okay, let's keep going. Here's part B. Play when you're ready. So here you have a piecewise function. So usually when you're dealing with continuity and a piecewise function, this right here, the conditions, I call this the value of interest. Okay? You focus on that value. So you go down the list. Is f of 0 defined? Okay? When x is exactly 0 here, which function do I use? Do I use the top one or the bottom one, right? When x is exactly 0. So in this case, we would use the bottom function. So f of 0 is 1. So it passes the first test. So we move on to the next one. We have to find out the limit of this function as x approaches 0 exists. So if you're approaching 0, which function do you look at? Do you look at the top function or do you look at the bottom function? Okay, so it goes all the way back to day 1, you guys. A limit is when you get arbitrarily close but not exact. So here you would actually use the top function. Okay. And then here you have a few different ways of analyzing this here. You could use the numerical approach, which I don't recommend. Graphical approach if you have the access, or analytical. So let me do this with you guys. So first thing, direct substitution, you try to plug it in. 1 over 0 squared, you know that's going to be undefined. So what happens if you can't substitute? Okay, look back at your notes if you need to. We would have to try to manipulate this somehow. But if you take a look at this function, 1 over x squared, there's not a lot you could do. There's no conjugate. There's no difference of two squares. There's no LCD. There's not a lot you can do here. So this means that it doesn't exist. Because you can't do much, it doesn't exist. And that's not the best explanation, but the graphical explanation is probably better in this case. And I'll show you here. 1 over x squared, and if you have access to it, it looks a little bit like this. If you could tell right here, as x approaches 0 from both ends, they both go all the way up to infinity. But remember, infinity is not a value, which is why it doesn't exist. Okay, so there you go. It breaks the second condition, so we don't even have to look at the third condition. So we know that it's discontinuous, therefore f is discontinuous at x equals 0 since the limit of f of x as x approaches 0 does not exist. Make sure you guys are comfortable with explaining, okay? As by they I mean the AP exam, as well as my final and exams as well. I look for a lot of explanation and clarity, okay? Don't just say f is discontinuous since it doesn't exist, okay? You want to be very specific. F is discontinuous at x equals 0 since the limit as x approaches 0 doesn't exist, okay? Practice that. There's your picture. It's defined, but the limit didn't exist. Okay? Here's another one. Part C, I think, or D. I always lose track. But here we go. Write it down. Okay, so we go down the list. Our value of interest here is, in this case, 2. So let's check. Condition number 1 is f of 2 defined? Okay, in this case, it is. When x is exactly 2, it's 1. When x is exactly 2, it's 1. So it passes the first test. So now we have to check the second test, which is, well, is the limit as x approaches 2, does that exist? Okay? So if we're dealing with the limit, when we're getting arbitrarily close, we should deal with the first function, because we don't want to deal with what happens when x is exactly 2, okay? So here, this is the limit as x approaches 2 of x squared minus x minus 2 all over x minus 2. Okay, so you guys have a limit now. What do we do? First thing when you see a limit, you try to substitute. But I won't write it down here. I noticed that when I plug in 2 mentally, the bottom's going to go out to 0, so I have to come up with another way. I noticed that up top, okay, whenever I see quadratics, I think of this right away. Can I factor it? And in this case, you can. I'll give you a second. Play when you're ready. This comes out to x minus 2, x plus 1. And since I didn't take the limit yet, I'll bring that guy over. I'll squeeze that in there. Did that help us in any way? It did. We could actually reduce the x minus 2 factor, and we're left with the limit of x plus 1 as x approaches 2. And then I repeat. I try to plug in chug, and I happen to get 3. So it does exist. Okay? So it passes the first test, the second test. Now what's the third test? Does the limit as x approaches 2 equate to the defined function? Okay, so the limit came out to 3. The defined function came out to 1. Are they equal? They are not equal, so it doesn't work here. Therefore, pause and then play. F is discontinuous at x equals 2 since the limit of f of x as x approaches 2 does not equal f of 2. Okay? Think about what that looks like visually. How can a limit exist but be defined somewhere else? Okay? And I'm hoping you're coming up with a similar picture here. You can have a limit that exists but be defined somewhere else. Now, that's probably not how the picture looks like, but it's something of the same nature. Here it is. So you have a graph where the limit does exist, but it's defined somewhere else, which is why you had to lift up your pencil. Okay? Okay, so graphically, there are 3 types of discontinuity. Just remember HIJ, the alphabet. Whole, infinite, and jump. Okay, I'll show you all three. Whole is often known as a removable discontinuity. Infinite is when you have asymptotes. And a jump is literally when you are jumping from one value to another. Okay? So here we go. Go ahead and draw this out here. My very clean sketch. We're going to identify it, okay? And I'm just going to call this, let's call this A, B, C, and D. Okay? So I'm showing you that it's discontinuous, and I think you'll agree. It's discontinuous at A, B, C, and D. Very casually, we had to lift up our pencil or pen at A, B, C, and D. Okay? Now, why? So here, what kind of discontinuity is that? Is that a whole, an infinite, or a jump? So here, this is definitely a jump discontinuity. I had to jump to a different value. Okay? At B, there's just a hole. Because you continue at the same spot, right? It's not really a jump. Now, C, even though there's a defined point there, you would still consider this as a hole and not a jump. Okay? Kind of weird. Now, part D is your infinite because you approached an asymptote and then you had to continue right after that asymptote. It happens to be down here. Okay? Nothing too complex. You just have to identify it, know what type of discontinuity it is. Okay? So basically here, for a jump discontinuity, let me erase this now. Let's go back and identify it through our rules numbers 1, 2, and 3. Okay, take a look at A now. What rule did it break? Number 1, 2, or 3? Go ahead and pause and play when you're ready. Okay, so in part A, it's discontinuous because it didn't break rule number 1, because rule number 1, it is defined there. But the limit didn't exist, so that's actually number 2. Okay, the limit did not exist because notice how it's approaching two very different y values. Okay, let's take a look at part B. Part B broke rule number 1. It's not even defined. Okay, part C has a defined value. The limits do exist, but the limits did not equal the defined function. So here it broke rule number 3. And part D, since there's an asymptote there, means you can never get there. It breaks rule number 1. It's never defined. Okay? So if you've noticed, hopefully you notice what I'm doing here is I'm helping you understand a concept through many different lenses, okay? Not only just algebraically, but graphically and numerically as well, okay? All right, so don't write this part down. I'll show you how to sum this up here. This theorem states that the following types of functions are continuous at every number in their domains, and then they listed a bunch. I'm going to have you guys write this instead. Generally, and I use this very loosely, okay? Generally, any function, there are exceptions, but not in this course, okay? Generally, any function is continuous on its domain, okay? Whether you're coming from pre-cal or IM3, you should have discussed domain, but let me refresh anyways, okay? The domain is the set of all possible x values, okay? So instead of thinking about what's possible, think about all the values that make it impossible, right? So there are two things generally that can go wrong with a function, okay? So there are two big no-nos in math, okay? you cannot divide by 0. Okay, or else it'll be undefined. So whenever you have a fraction of some sort or a rational function, which is fancy for fraction, you know that there could be a chance that something could go wrong, okay? So we're looking for fractions, okay? Something else that can go wrong in math is when you're dealing with even roots, but in this case, it's really just the square root. What can go wrong in a square root, right? You can square root some type of negative number, causing it to be imaginary or complex. All right, so I'm going to show you guys how to find domain very quickly by looking at fractions and square roots. Okay? Because if we can figure out what values don't work, we can figure out what values do work. And all the values that do work will always be continuous. Okay? Any function will be continuous on its domain. So as long as we're using a value that's in the domain of the function, it will always be continuous. Okay? It sounds like a lot, but it's not. Okay? So here we go. Let's practice this. Example, gosh, I want to say 3, but let's just call this 5 because I lose track of my numbers. Okay? So here we go. The first thing you want to do is, if I gave you a limit problem, right? What do? I taught you guys to first plug it in first. Okay, so we're going to plug in -2. Notice how I'm using parentheses. Okay, so here, -2 cubed, I'll get -8. -2 squared is 4 times 2 is 8. And down below, I'll get 5 plus 6. Basically, you're going to get -1 over 11. Okay, so I tried to plug in this number, and it worked. I didn't have to manipulate. Now, I want you guys to think about that. Why did I not have to manipulate, right? Okay, so here's what's happening behind the scenes, okay? You're looking for two things. You're looking for fractions, and you're looking for roots, okay? This problem does not have square roots, but it does have a fraction, okay? What can go wrong in a fraction, right? The denominator can go to 0. So think about that. If I made this go to 0, if I solve for this here, okay? And pause if you need to figure that out. If x is 5/3, if I plug in 5/3 for x, this thing will go to 0. And if it's 0 at the bottom, it's going to be undefined, right? So look, as long as I'm not approaching 5/3, direct substitution will always work. Since -2 is not 5/3, I know I'm going to get a value out of it. And that's the reason why it works, because of the notion of continuity. Okay? So how do I actually put it into play? This was really just to explain to you guys how it works, okay? So look, here's example 6. Play when you're ready, but write this down. On what intervals is each function continuous? So here they give us a function. So let's approach it this way. You look at this function and you ask yourself, I'll do a little thought bubble, are there fractions? Are there square roots? Okay. Are there fractions? No, we don't have any fractions here. Are there any square roots? No, we don't have those either. So look, if you don't have any of these here, you're not going to have any restrictions. That means the domain, you could use any number you want. That's called all real numbers. or the fancy R if you've seen that. Okay? So here, the question says, on what intervals is each function continuous? So we're going to be a little bit sly about it. Because we know the domain is all real numbers and all functions are continuous on the domain, then we will know where this function is continuous. So f is continuous on all real numbers. I like to write interval notation. Some people like to use the fancy R, but then again, that's not always the case. So I encourage you guys to write interval notation there. Okay? So notice how I didn't have to use all three conditions. So this is kind of like the backdoor entrance to explaining how continuity works. Okay? Let's do a couple more. Here's part B. Play when ready. Okay. We have to figure out where the function is continuous. So before we do, let's think about domain. So our thought bubble, right? Do we have square roots? We do not. Do we have fractions? We actually do. So could something go wrong? It could. So what you do here is you focus on the denominator. You imagine if it came out to 0. So you set your denominator equal to 0 and you solve. And eventually, don't forget when you square root, you get a plus or a minus, okay? Plus or a minus 1. So what this is saying is if x is 1 or negative 1, what would happen to the bottom? It would come out to 0, causing the whole function to be undefined, right? So we know that our domain has to be all real numbers except for these two numbers. Okay? So we know if we know the domain, we will know where it's continuous. So we'll say G is continuous, and I'll show you several ways of writing this, okay? On all real numbers except x equals plus or minus 1. In most multiple choices, they'll write it like this, is continuous from negative infinity to infinity. But what you guys have to do is you have to omit the negative and the positive 1. So just imagine, if you will, even though infinity and negative infinity is not a destination, I'll just put it here. Right? So everywhere in purple is going to be continuous, except when you get to what number, right? When you get to negative 1, and then when you get to 1. So really what you have to do is you got to hop over it, continue, hop over it, and then continue some more. So the way you would write that is we're going to go from negative infinity to negative 1 parentheses, which just means you get really close but not exact. Does that sound familiar, you guys, when you get really close but not exact? It's like a limit, okay? And then you're going to hop right after negative 1, and you're going to walk all the way to 1, really close but not exact. And then you're going to continue right after 1 all the way to infinity. Now, although the first statement is easier to write, this is the more common way of seeing it on an exam. So please get comfortable with both. Okay? Cool. Here's part C. Here we go. So do we have square roots? We do. We have square roots right here. Do we have fractions? We do. We have a lot going on here, okay? So let's deal with the square roots. Sorry, let's deal with the fractions first, okay? So we want to make sure that we cover our denominators. We set those equal to 0. Okay? So right here, I know that x is going to come out to 1 if you solve it. Over here, I'll do this quickly. X squared equals negative 1. I end up square rooting, but then I deal with something imaginary, so it's not defined here. Okay? Here's what this means, you guys. Really, if you think about it, if you take any number and you square it and you add 1 to it, there's no way that it's going to go to 0. Because if you square a number, it's never going to be negative. It's always going to be positive, right? In most cases. So that's the reason why you're getting something funky here. So we actually don't have to worry about this denominator, okay? Because there's nothing that can go wrong there, all right? So we know that x can't be 1, okay? But then let's deal with this square root, okay? We know that the radicand, and let me give you some background. A radicand is everything inside the radical. So in this case, the radicand is just x. You're going to set your radicand greater than or equal to 0. Okay? Think about that. What numbers are greater than 0? Right? Positive numbers. Okay? Positive and 0. So what we're doing here is we're not letting this be less than 0, because numbers that are less than 0 become negative. So we're making sure that this radicand stays either 0 or positive, okay? So every time you have a square root, you take your radicand and you set it greater than or equal to 0. This one is simple enough to where it's solved. So here, this right here is all numbers that are greater than or equal to 0. The way you would write that is 0 bracket, use a bracket because it's or equal to, so you want to include it, and you would go all the way to infinity. These are all positive numbers including 0, okay? But you got to remember, x can't be 1. So if you start at 0 and you go all the way to infinity, will you guys ever reach the number 1? You will. So what you have to do is you have to avoid it. So you have to start at 0, and then you have to get really close to 1, hop over it, and then continue. So think about how you would write that notation, okay? I'll start this one off. F is continuous at, I should use at, from, or on. So we start at 0. Remember, we could include 0. We're going to get arbitrarily close to 1. So I'll use parentheses, union, and then I'll start at 1 again, and I'll go all the way to infinity. Okay, get comfortable with interval notation. They use it a lot. But the concept itself of just looking for a domain, very simple to do with practice, okay? Let's see. I'm thinking about what we have time for. Let's do this one. Okay. Let's call this example, 8. You could ask my previous students. I always forget the numbers. Okay. So here, I didn't write the instructions, okay? But we're going to try to find out where f is continuous. Okay? So it gets a little tricky because now you're dealing with a piecewise function. You guys will see this a lot. Okay? So get used to it. Don't freak out because it's a piecewise function. Now, separately, negative 2x plus 3 does not have fractions or square roots, so we don't have to worry about it. Now, separately, x squared does not have fractions or square roots either, so we're good. But what makes this different is that value of interest. Okay? So this is where you have to go back to the definition of continuity. Okay? So look back if you need to, but here we go. The first condition is let me backtrack, okay? So we were talking about domain. So we know it's going to be continuous in a lot of places, okay? The only thing in question is our value of interest is 1 continuous, okay? Is it continuous at x equals 1? Because that's where it breaks off, okay? So remember, a piecewise function could be a function that's broken up into pieces, right? And we don't know whether the pieces are connected or not connected. And where we're questioning it is at 1 here. So what we're going to do is we're going to try to figure out if f of 1 is defined. So think about this. When x is exactly 1, which function are you working with here? When x is exactly 1, right? If you see the little or equal to symbol right here, that's when x is exactly 1. So we actually have to plug it into that second function, which comes out to 1. We know it's defined. Not enough to show continuity yet, so we got to keep going. Step 2, what's step 2, right? We have to figure out if the limit as x approaches 1 exists. So here's the thing. Your conditions have a less than or a greater than, so it's directional. So we actually have to split this up into 2 different limits here. We want to approach 1 from the left, and then we want to approach 1 from the right, okay? And we want to see if these equal. So if we approach 1 from the left, again, what you're saying in your head is what number is to the left of 1, okay? That's like 0, -1, -2, -3. Pretty much any number that's less than 1. Remember, less than looks like an L. So here, we're plugging 1. I'll write it out, and you guys could find out where you can cut your corners. We're playing with that function right there as we approach it from the left. Now, if you approach it from the right, you're thinking of numbers greater than 1, which would then be this x squared function, okay? Even though there's a left and right directional limit, you just directly substitute. If you plug in 1, you should get 1 over here. If you plug in 1 on the right side, you should get 1 as well. And look at that, they do equal. Okay? So let me erase this real quick so we have space, but rewind if you guys need to and replay it. So now we know that the limit equals 1. So the last thing is, does the limit equal the defined function? Do they equal each other? They actually do. So what does that really tell us if all 3 tests passed, right? We know that f is continuous at x equals 1. And then we discussed before, we know it's going to be continuous everywhere else too. So actually, therefore, f is continuous on all real numbers. You can do the fancy R if you want, okay? Now, if one of these 3 conditions were broken, we would know that it would be discontinuous at 1. So then we would say f is continuous from -infinity all the way up to 1, and then from 1 to infinity, okay? So there are some obstacles that you have to go through. Usually, the value of interest is what you have to look at, okay? All right. I'll leave this here for you to try, okay? I'll pause there. Play when you're ready. F of 2 will come out to 2. Okay. The limit, let's see, the limit won't exist. So the limit as x approaches 2 from the left, which is this function here, you should get, 2. But if you check the limit as x approaches 2 from the right, you're dealing with the second function here. You should get 1, and notice how those 2 are not equal. Okay? You would make your conclusions there, okay? So therefore, you know it's discontinuous at 2. So you know that f is continuous everywhere else. So from negative infinity to 2 to infinity. That's really one for you to practice, which is why I'm rushing it so fast here, okay? All right, last part before we conclude our video. There are 3 big theorems in calculus. This is the first one. By big, I don't mean complex. It's a very simple theorem, okay? This is called the intermediate value theorem. Go ahead and write that down. Intermediate value theorem. Okay? And then here's the fancy talk, and you guys could write that down as well and play when you're ready, okay? Here, I am going to explain to you in a picture. Okay. So, here's a situation for you, a scenario, okay? I call this the birth height scenario. Okay? So let's suppose that this was time and this is height. All right? Let's say that when Jennifer, I'm just making up a name, Jennifer was born at 19 inches tall. So this is when she was born. Okay? At time 0, right? Okay? Now at 17 years, she is, 72 inches. Okay? As time goes on, now I don't know exactly how Jennifer grew, but you have to agree that she's either staying constant or she's increasing, right? But more importantly, at every single time, she has to be some particular height. And it really doesn't matter how you draw this. But I want you to notice that there's no way that I could have lifted up my pencil. Because there's no way that 1 second she's 4 feet and the next second she's 5 feet. It has to be a gradual growth, right? So continuity has to come into play here, all right? The function has to be continuous. Okay, so if a function is continuous, all right, here's what this means before I get to the theorem. So here are some true or false questions for you guys, okay? True or false, at some point in Jennifer's life, she was 32 inches tall. Okay, in which you guys would say that that's true. At some point in her life, she was 32 inches tall. Okay? Here's her next question. In true or false, okay? In some point in her life, she was 62.48 inches tall. Okay? Now, although that's very specific, it had to have been true because in order to go to 72 inches, you have to pass through 62.48 inches. Okay? So here's my point. True or false? In some point in Jennifer's life, she had to have hit every single inch and decimal in between 19 and 72 inches. Okay? And that right there is the intermediate value theorem. If you've ever played any video game, you know the intermediate means what, right? Middle. Okay? So Jennifer is guaranteed to have hit every single inch in between. Okay? Now, is Jennifer guaranteed to be 84 inches tall based on this graph? No, because 84 is exceeding the 72-inch mark, right? Now, based on this real situation, that's probably not plausible, okay? So here's what the intermediate value theorem says. It says that if you have any function that's continuous and it's closed, meaning the two endpoints are defined and closed, then you're guaranteed to hit every value in between, meaning there exists some value in between that. And that's all. Okay, it's a very simple theorem. I know it seems weird right now because you're not sure how to use it, but just think of the birth height scenario. Okay, intermediate value theorem, IVT, is the birth height scenario. Okay, you're guaranteed to hit every value in between. So how do we actually use this? And I'll conclude it for this example here. Okay. Call this example 9, write this down, play when you're ready, okay? Show that there is a root. Remember a root? If you don't remember, a root is where a graph hits the x-axis. That is called a root. Okay? So, show that there is a root for this equation between 1 and 2. Okay? So, here's what we're going to do. We're going to plug in 1 into our function. And you could do this by hand or use a calculator. I'll leave it up to you. I'll try to just do this here. Let's see. -2. I believe when you plug in 1, you get -1. I could be wrong. Let me double check that. 4 minus 6, 2 plus 1. Yep, okay. Now, if you plug in 2, oh gosh, I'm going to have to write this out. So you get 32 minus 24 plus 6 minus 2. That's going to be 8 plus 6 minus 2, which is 12. Okay. Okay, so here's what I want you to think about. Take a look at this here. If that is your function, if that orange highlight is your function, can you tell me where it's continuous? Okay, play when you're ready. This function, because it doesn't have any square roots or fractions, I know the domain is all real numbers, which implies that the function is always continuous. Okay, meaning I never lift up my pencil. Okay? So now I just figured out that at f of 1, it's -1, so somewhere down here. And at f of 2, it's somewhere at 12. This is not to scale, okay? Okay. So if at 1, I'm at -1, and if at 2, I'm at 12, am I guaranteed to have a root in between? Okay? Since I know the function is continuous, take a look at this, okay? I don't know exactly what happens in between, but I know that it's continuous, meaning that some way or another, this could travel like that, or I don't know, like this. I really don't know what happens with this graph, but in all 4 different cases, whether you're looking at the light green, the dark green, the orange, or the blue, notice that you're guaranteed to cross the x-axis, which is what a root is. You're guaranteed, okay? So, why are we guaranteed that? Based on what, right? Based on IVT, okay? So, here's how you guys would write it. Since f is continuous, from 1 to 2. It's really all real numbers, but from 1 to 2. And f of 1 equals negative 1, and f of 2 equals 12 by IVT. There exists a C in somewhere between 1 and 2 such that f of C equals 0. And I put 0 because it's a root. Okay? Now look, you guys are not going to get comfortable writing this unless you practice. Okay? It may look a little bit new, but you got to keep practicing until it gets good. Okay? We don't know exactly where the root is. We can just prove, we can guarantee that eventually this graph will cross the x-axis. Okay? We can guarantee the existence. All right? So, on the last note, before I conclude this video, what we're really looking for is if we know that we have some type of negative value and some type of positive value, in order to switch signs, you're going to have to cross 0. Okay? I'll leave this one here for you guys to try out. But that's it for the video. Practice on your homework. Please text me. There's no dumb questions. Whether it's small or big, ask the question, okay? I'll be happy to clarify, and best of luck.